Yacht a binne. It is early morning here in Minneapolis, Minnesota. Ado shilski the binne. I wanted to talk about some questions about some things that people have been asking very frequent. This is somewhat of a informal session here about what I've been doing in the recent years. Also, what does it mean to do PhD work? Well, maybe not too deep, but basically there is some informal drawings I made here I'd like to show in a moment as well. But what I've done here is kind of give a quick rundown through some hand drawings that I've made and I've shared with some friends recently. We'll get there. We'll have a more formal session in the future, actually, with some colleagues of mine or perhaps with some organizations like Quantum Grad and so forth, of how these kind of explorations work. So let's get to it real quick. All right, so let's look at this real quick. So basically, as a summary, another hand-drawn set of words here. I went from being a carpenter to being an electric vehicle researcher to a quantum mechanic with publications and things like that in the field of condensed matter physics and things that pertain to these applied physics fields. But it's also electrical engineering related. It's very interdisciplinary. Anyways, so in the beginning, I did a lot of carpentry there on the Navajo Nation. We call it Dinebekeya. It's a place I come from in the state of Arizona, here in the US. And, well, on the countryside there, we have a fairly peaceful life. It is somewhat lawless where I live, but regardless, you just enjoy nature, survive. Cost of living is fairly low, actually. And this is here in the US. But I did a lot of carpentry there because we have forests. We have to maintain the trees, the dead trees there, or should I say, maintain the forest there to prevent the forest fires. Because Arizona is a fairly dry place, even though we have forests and all. But there in the mountains, we have all these trees, right? So there's a little tree for you. Very simple tree. And then there's like some other trees like this, right? And then trees, they do live pretty long. I'm kidding, no doubt about it. But the trees can also die. They can get withered, or they can, well, not really withered, they dry out when they die. That's the thing. And it becomes a fire hazard. So maybe you can pick a different color here. It becomes a fire hazard. It's a problem because what happens when we have thunderstorms and weather that causes the lightning to come, right? You get lightning, strikes the tree, causes forest fire. That's no good. We don't want that, right? So that's the thing. Carpentry is a fairly sustainable practice, and you can prevent these things. Only you can prevent wildfires, as the great Smokey the Bear once said. So that brings us back to the journey. So as a child, as a young man, did a lot of carpentry there in the mountains, and up until I was about 18 or so, then I graduated from high school. I did get invited to some institutions here in the US as a child, even before I turned 18. And they wanted to send me there to those universities to do training. But I said no. I said, let me wait. I'm too young to just leave the mountains. I can't just go. It's not. Like, what are we gonna do, right? Like, I build things. How am I supposed to build stuff on my own in laboratories as such if, child labor laws get in the way, things like that. You don't want to deal with those kind of things. You have to wait until you're about 18. Then you can work. You can actually work on the hardware. That's actually why a lot of young people today, when they get trained at the universities, even below 18-year-olds, like 16, 15, 14, all the way down to as young as you want, really. If you have the mindset to work or do work at the university level as a child, then most likely that child is going to be contributing to the field of that's somewhat theoretical or has something to do with computer software, because if you work on computer software, then you can get credit for it or points or something like that, some sort of incentive as a child below this range. Then you're not technically doing any serious hard labor that's going to interfere with it. Anyways, regardless, when you do turn 18, you can then have a chance to work on the real physical hardware and get paid for that. And then you can be sent to these fellowships based on how well you network with people and how well you communicate your ideas, things like that. So that's what happened to me as a young man. And then I got sent from one fellowship to the next on these non-tribal laboratories. So carpentry, that's something I did on the tribe. So this is tribal. It's more like a tribal practice. You can be a tribal carpenter. You can be a tribal farmer. You can be a tribal, maybe politician or something else, something social related, or maybe go into the health field or something like that. It's usually more like, or maybe like a teacher, something like that. You can do that when you're fairly young there on the tribe. And when I say young, I mean, of course, of working age. But that's usually what people do there on the tribe. They go into these kind of work. That's, well, it's not a, I mean, we don't live in a city, so it's not like we have a ton of jobs, but, we get by. We keep ourselves busy. But on the other hand, if you go and get sent to a university or some other institution that will provide some sort of advanced training, such as in nanotechnology or maybe somewhere in the range of like robotics or electric vehicle research, then that's possible. So that's what happened to me. I got involved in electric vehicle research. I built electric vehicles for them at the university. I was 18, and then I turned 19. I was working there. I built them big electric vehicles. I have pictures for that I can show you later. And then after that, they sent me to that fellowship here in Minnesota. That is a nanotechnology fellowship. But then by that time, they gave me what is called an associate degree. It's a 2-year degree. So we went from there, and then we went to, they allowed me to work in the laboratories here. And then while I was doing that, I decided to join a bachelor's degree program. They call it a MDS. It's multidisciplinary because I had multiple interests at the time. And then that was just sort of extracurricular studies for me, because research does not require you to study a specific set of topics. You know what I mean? Like, you can if you want. You really want to focus only on one area, like maybe physics, for example. Then you can study just nothing but physics for many years, or for a 4-year degree program. You can do that. It's possible. But that's not the only option. You can do something multidisciplinary and then finish a 4-year degree in that, such as what I did here. Did architecture because I had some carpentry background, and then I went into communication studies, and then this is just like people communication, right? And then some physics mixed together with physical sciences and things like that. And then that was good enough for me. And I just kept working in the laboratory, working on these nano chips, quantum-based nanochips. Nanochips that have quantum functions, I should say that. And that's what I did for those years. And after that was finished, the next thing to do was either to go to work in the field at this point, right? You get to this point, I have a decision to make. So think of it as the path going from here, stopping by here, and then going here, and then from there, continue on, and you get to this point, right? And then you have a decision to make. You can either go into a graduate program, like PhD program, or go directly work somewhere in the field. Let's just say there's a box here, a mystery box. Who knows what that mystery box holds? But I'm trying to draw a question mark here. So that's what happened. I was convinced. I was motivated, or should I say, encouraged by the faculty at the university as a young man, because I had all this training like this, and then training in nanotechnology, and training with some level of quantum. And so they said, well, we can put you in a PhD program. And I said, okay. And they said, well, we'll pay you for it. So they did. I was like, you know what? Why not? Then I did. And I realized that actually there's so many things you can do with a PhD. Only if you know how to use it, of course. You can expand on the field some months with some degree of flexibility. So in this case, I focused on quantum hardware using nanotechnology. And the interesting thing here is that you can work on quantum hardware without actually having to be an expert in classical physics. This is a question you can ask anyone in the field of quantum hardware, or you could ask a real, or should I say, another scientists besides myself. You can go and ask them, those that have PhD or professors in the field of quantum, even theoretical physics, theoretical quantum physics or condensed matter, things like that. They can tell you that classical physics is you can have some ground understanding, some base understanding of what's happening here, but because quantum physics does not rely on it, you can kind of jump over it in a sense and get directly into the mechanics, the quantum mechanics here, quantum physics. And then from there, pretty much the only things you have to really focus on are pretty much waves. Waves, like what are atoms made of, what do atoms do, energies, Hamiltonians, things like that. Then from there, you can turn that into quantum engineering. So quantum engineering, of course, is like you're playing with atoms that have a certain kind of structure. I drew a little arranged dot here, kind of to behave like a set of crystals, crystalline structure, or a set of randomized structure of atoms, in which we call it amorphous. Regardless, you can deal with that and measure things in it, energies, resonances, physical properties, and so forth. So I tend to use Legos to try to represent those, or little dots. But having this so-called Lego mindset is something you can do as well to help you really try to get a grasp of how to manipulate quantum matter and quantum effects in these devices, real physical hardware. So that brings you to the quantum hardware stack. So there's this thing called a quantum hardware stack. And you're really dealing with analog equipment, waveform control, interfaces, and then at the very bottom of this so-called quantum hardware stack, or hardware stack for short, then you have this quantum processor, which has the quantum devices on it. So the devices, of course, they're made up of some arrangement of atoms. It could be, a piece of glass, or it could be a piece of metal, or some other exotic material. And then you can do quantum hardware engineering or quantum engineering. So that's what's possible with all this kind of work, really. And like I said, you don't necessarily have to rely on the classical understanding to do that. Just waves, and then how do you manipulate waves to do certain things, and then how do you try to understand that using all of these mathematics like linear algebra, for example, which tends to have a lot of so-called matrix representations, and then among other things. So, in other words, you do quantum hardware engineering, you end up working with stuff like this. And I believe in classical physics, it's more like a range of other things that are not as flexible as you would have in certain areas with quantum hardware. So, let a classical physicist explain that to you. I don't have too much expertise in this area. I kind of explored it just a little bit, but I focused on the nanotechnology and the quantum hardware myself. There are plenty of, there's plenty of resources. There's plenty of training available for you in that area if you want. That's up to you. And then, of course, later on in life, you can always look back, right? If you feel like going back here and exploring some of the more classical related mechanisms in physics, then that's up to you. You can do that later in life. You don't have to do everything here to get to this point. You can kind of make your way around and make your own path, and then explore as much as you want. That's all it really is. And then you can become a quantum mechanic. So that's what happened for me, and here I am. I'm no longer in the first year. I'm actually in the second year now. So second year of PhD work. And of course, I got Google Scholar page and things like that. You can see what the publications look like. But yeah, let's get back to what else I can explore here. Oh, somebody's asking questions. Sorry, I didn't realize you guys were asking questions. Sorry about that. So, okay, so someone says, will quantum computer be available for the general public? Yes, they exist already. Actually, I can show you some slides if you'd like. Let me bring it up here in a moment. So I have a PowerPoint presentation because in the PhD work I give lots of presentations in the field, and I give invited lectures, things like that. And I show them my quantum chips. So like I have some quantum chips here with me that I keep on hand, and I build these myself. I design them myself. I encode them, and I train PhD students. I train postdocs on how to do these things, because these are very specialized skills. It's not something that you can easily learn from a classroom. You can't sit there in front of a whiteboard and say, okay, now I understand how to build a chip. You have to actually go in the laboratory and then receive the training. So I'm the person delivering that training in the nanofabrication facility. So that's kind of one of my specialties as well, which is called nanofabrication engineering. But like I was saying, I'm going to show you some slides here of some quantum computer devices, quantum computing desktops. So there is a presentation I would like to bring up here. Let me look for it. Own the intellectual property of the chips that you made. Yes, I do. I made it Creative Commons. So let me write it on the screen since I'm still sharing the screen. There's this wonderful thing that I would like to give a talk about in the future, which is really really amazing, which is called Creative Commons. Creative. See, I can't draw this fast enough because I'm using a mouse to draw it. But there's this thing called Creative Commons. Creative Commons. And the S. So there's this thing called Creative Commons, and basically you can create anything you want and basically stamp this license on there, and that it's officially yours. And if it's original, of course, you made it on your own. Like for example, I'm showing this drawing here. This is my drawing. This is my handwriting. With the exception of maybe this part, we don't know who that belongs to. That was just out in public. But mostly this part here. I can say that I'm allowing the public to redistribute, share, alike, and things like that. I'm giving permission to the general public to use this for whatever purpose they feel like. And that's called a Creative Commons license. So that's one thing I want to say or want to mention. Oh, I thought I was sharing the screen. Hold on. Let me share the screen again. Here we go. So, as I was saying, there's this thing called Creative Commons. I drew it here. And Creative Commons is a stamp of approval you can place on any document that has intellectual property that belongs to you. And there's another one called Open Hardware License. It's called a CERN Open Hardware License. Trying to, you know what? Let me erase it over it. There we go. It's called a CERN Open Hardware License. CERN. CERN Open Hardware License. I'm just abbreviating it. But that license is very much similar to Creative Commons, except that this is for hardware. So you can build a physical chip like this one here, or a machine that's your own design. You made it yourself, things like that. You can slap a sticker on there that says, this is licensed by me, and this is my creation. Therefore, if you acknowledge it to the world on some piece of paper and put a date on there, or maybe if you share it online like what we're doing now, then there's already a date recorded on the screen somewhere, or on the picture. You will then be the original owner or the original designer of that thing. So that's what I want to say, is you can do some pretty cool things with Open Hardware License and Creative Commons. Yes. Let's see here. What else can I share? I wanted to share something about quantum hardware here in a moment, because someone was asking a question about it. Let me put that here. Open Hardware tutorial. So let me see. Cryogenic. Ah, yes, I found it. So I'm gonna share a slide. Okay, so this is one of the many presentations that I've created, right? And this thing right here I'm showing you on the screen is what we call a licensed or a Creative Commons licensed picture. So this picture I borrowed it from a website called Flickr, and if you slap a Creative Commons sticker on there, on the title within where this file is located, then you can see that the intellectual property is available for people to use freely. Of course, you can put as much limitation on there as you want. That's what I'm saying. And if you want people to use it for specific purpose, like art or something like that, And if you want to say, oh no, please do not use this to build on something that is commercial, like don't commercialize my design, then you can say that in the license. There are so many licenses, sub licenses. Anyways, let's get back to this. So this is a very professional presentation, but here I show a 3D model of a computer. So this is a just very basic, generic 3D model I made to represent a desktop computer. And then here's some 3D models of server machines or server clusters, server farms of these units here that you can place into a big data warehouse or data center, right? And this is usually how supercomputers are set up. And quantum computers these days, they're typically built like that. So here you can see that there is a quantum computer that is set up at IBM, very similar to this, but this one's planned for the coming years. This is called the IBM System 2. And then I will show you more on this in a bit. But here on the left side, you can see that there is this quantum desktop that you can buy for $5,000. So this exists on the market. This is more of a novelty, and it gives you up to about 3 qubits. So you can have a 3-qubit system in this desktop, and everything, all the control components and everything is contained within this desktop component. And you can plug it into a monitor. It's a real product you can buy. There are more pictures of this, but you can pay for that with $5,000, and then you can have it in your own house, your own classroom, lab, whatever you want. So we have also quantum control hardware that exists. So there are companies like Q-Blocks. There's Zurich Instruments that also makes similar hardware, and who else? Another one from TU Delft. Of course, I can't list all the machines, but that's one of them. And let's see. I'm going to show you a different presentation here in a moment. There's another one I have, which is related to quantum hardware. So this one is another quantum hardware presentation I made. It's a PhD presentation. This is some more pictures of the energy grid. Let me stop screen sharing real quick and then reshare the window I'm trying to show. So let me show you this one. Okay, here we go. So there's this one, another PhD presentation of mine, and I was showing that you can have a supercomputer like this that exists. These are server clusters, and this machine's called a Cray supercomputer, and it's powered by 21 megawatts. So basically you need a small power generating station of its own dedicated to run this machine, and you have to have it running over 24/7, and it might not always reach 21 megawatts, but it's on that same level of power consumption. So that's a lot of electricity you're burning just to keep this machine doing its work, doing its maximum work, perhaps. And when we talk about the upgrades, we're expected to achieve like 60 megawatts in this year from a bigger machine, which is more of an upgrade. And then on the other hand, we have these quantum computers here, actually, that exist in the laboratory. So these are real pictures. These are not renders or anything. But here, this one uses about 50 kilowatts, and we're expected to get the upgrade of the quantum system to a system 2, which will consume less than 140 kilowatts, and that's a huge upgrade. Yet it still remains in the kilowatt range, which you do not need a custom power generating station for compared to this one. You might, I mean, you could probably set up a couple solar panels or like a small solar field for this, and then it's good enough. And a battery bank, some battery banks. But that's what I'm saying is that you can buy quantum computing components and then build your own qubits at home if you'd like. And you can use hardware like this one right here. This is Flipper Zero, so more of a hacking device. But the functions of this software-defined radio, I wrote that here, the software-defined radio transceiver, you can do wireless control, or you can do wired control, plug it into the interface, and then you can record signals and then use those signals to modify whatever the target is. In this case, quote unquote, hacking. Or, well, it really is hacking using hardware. And in this case, if you wanted to build a quantum processor on your own and you know how to do it, like in the laboratory, then you can do that with this machine, this little piece of hardware, Flipper Zero. So a friend of mine let me borrow one of these, and I have it here. I'll plug it in, and you will see what the Flipper Zero looks like. So the Flipper Zero looks very much like this. It's a little piece of hardware. You can plug some interfaces here, and then you can copy the codes from the real quantum computer. So if you want to hack a quantum computer, this is the way to do it. But you have to physically be there in front of the machine and to do things with it. So that's the thing about quantum hardware. We have equipment to control and manipulate all of these waveforms like this. So this is, I'm showing you, there are different waveforms that exist for various kinds of qubits. There are hybrid qubits that contain quantum dots and superconducting components, perhaps. And we have exchange-only based qubits, which is kind of like quantum dots and magnetics and things like that. And we also have single triplet qubits. These are all spin-based qubits. They have some kind of semiconductor component, and we are trying to control the electron spin inside of those qubits. And then we can, of course, view the more common superconducting qubits waveforms. So these you can compare the various waveforms that come off of the qubit. So you can see that here, if you have some qubit device here in the middle, then you can read a signal that's coming from the qubit, and the qubit will send a response. So you send a signal into the qubit, and then the qubit will respond. It's kind of like a brain cell. So I use this analogy fairly often, where in the human brain, you have all these electrical spikes, impulses, and you can measure the impulses again and again and again. You can see these tiny pulses like so, and you can measure them with these little electrode pads, or you can even use magnetic or an array of nanomagnets to measure these electrical impulses, or, well, in this case, magnetic fields that are forming from the flow of electricity in the neurons. You can do that. It's possible. And then you can interact with the neuron. So the neuron will fire a response back. So that's all it's doing. And that's how our brain works. Our brain is networking with each other, and we have this really complex system of memories and decisions and so many things that the brain is, so many different kinds of linkages in the brain to form all these memories. But you can talk to a neurologist or a biologist if you want to know more about that. They can confirm it for you. We have a quantum computer that you can use in the laboratory like this, and a very similar setup to this you can find in a magnetics laboratory like this one, and the same goes for a sort of neuroengineering laboratory. They have a very similar setup. I have some pictures of that because I've been in the laboratory. I've worked in such a laboratory in the past where we built brain chips. It's very similar. The only thing is, of course, this neuron is not necessarily being used as a qubit. This is just an analogy because it's a living object. For qubits, real qubits themselves, like, let me see here. I can show you an example right here. Here's a piece of wires that are interacting with each other using resonance and things like that. We can make these qubits interact with each other and couple them and create quantum gates, a 2-qubit quantum gate in this case. And then we can do waveform control, and you can measure the waveforms that will respond from the qubit. And then you can extract the energies and things like that to do quantum computing. So that's all it is. That's really all it is. And then you can turn it into some really complex network like this in a chip, and then build your own quantum computer. So that's where we're at. And this is Intel Horseshoe's chip. It's a quantum chip. And then we can take it further and build a chiplet which has multiple cores, quantum cores. So that's all I'm showing for today. It's a lot of work, but once you get involved in it, you can do so many things. You can take your interests as far as you'd like. Oh, people were asking questions again. What did I miss? It says important. Okay. If you work for a company. Yeah, well, this is a research institution. What we share is ultimately decided by us as the scientists. We're not run by a corporation that decides these things, or national laboratory. So if you work in a government laboratory, this is not a government laboratory, by the way. But if you work in a government laboratory, then they have more strict requirements and really like non-disclosure agreements, things like that you have to pay attention to. But here at the university, it's more open source. And then of course there are some that are more private, but the lectures that I give are usually not private. So yeah, I'm just going over some things here, kind of to give you an idea of what's going on and what the path is like doing PhD work. Yeah, and hopefully answers some of the questions, the immediate questions on the feed. Okay, what else can I show? I've showed them a lot of things. Oh no. The drawing that I made is pretty much stuck the way it is. I can't erase anything on it. It's fine. I have other copies. Yes, no problem. I think I explained everything I was trying to explain. That's yeah, pretty much it. The other thing I've wanted to mention is that recently I wrote a document on GitHub. It's free, but I added some more of the contents here. So this is something I'll show you here in a moment. Overleaf. Okay, so I'll show you the overleaf document. So overleaf is a LaTeX editor. So you can draw, you can create pieces of code on LaTeX. So let me show LaTeX. Okay, so here's LaTeX. LaTeX is a place, like I said, you can write some code, and then you can create fonts, words, clickable links, things like that. So I wrote this one. This is everything you need for experimental quantum hardware engineering. So you can do, I made this so that you can do a whole PhD with it. So I wrote that here. It's been useful to me in my PhD work. And basically, like I said, I went from being a carpenter to an electric vehicle researcher. And then I went into being a quantum engineer, quantum hardware engineer. In other words, a quantum mechanic. That's more of a, this is more of a widely used term to describe a person in such a field. And everything, again, is open hardware license, or it's used, it's licensed with Creative Commons to make it more useful to the public. So this is open source. Yep. And then a lot of open access quantum device tools, training videos I have available here, at a graduate level, PhD level training videos if you want. Less mathematical. I mean, I have some mathematical stuff on here if you want, but you can totally avoid watching those and focus more on the training videos that are focused on the physical hardware. And then I have the books and references for hardware as well, quantum hardware. And then I have examples of quantum hardware lab galleries, quantum applicable degrees that range from the bachelor degree level up to PhD level. And then we have curriculum, quantum science curriculum, which is related to all of this, all of these items in the list. And then I have quantum career opportunities available as well, listed here. So like here, I have some, I mean, these are all clickable links, but these are all open source tools that you can use to design the qubits themselves. So initially, if you know how to build a qubit yourself, then you can use this open source software right here called K-Layout. There's another one called Layout Editor, but K-Layout is a bit more flexible. And here you can use that to design the pattern for the qubits. You can download it directly from here. So look, I can click on it and it'll take me directly there. And then there are some device simulation tools here that are, I mean, this is widely used in the industry, but this is also open source. You don't have to download anything, actually. It's browser based. And then some others, finite element analysis tools that we can use to analyze the qubit design. And we can do all these other things. These are all PhD level materials that you can use, graduate level materials. And then here's this one I did. So my quantum chip that I made myself, and this is more of a side project, but it's really there to demonstrate and to show you how to create and use the codes that I wrote, the protocols that I wrote and I made for these machines in the laboratory, in a cleaner laboratory. Let's say you had access to a hardware laboratory in a facility that can build nano devices or nano machines. Then you can take this there and you can generate a pattern of qubit devices. And in this example, I made 400 qubits into an array, and then I placed that into a software, the layout software, similar to K-Layout. And from there, I use that to create other codes that I'm trained on and build a quantum chip. So that quantum chip is the one this one right here that I'm talking about, this quantum device. These are more like a placeholder because I don't plan on using this in the experiment. This is more of a demonstration for lithography. For the real quantum device, I am working on a patent for that one soon. So I'm not going to show that one just yet. It's going to take a while. But that one is actually part of my PhD work. The one that I'm talking about on the side. And of course, I have some other tutorials for that, for how to use the software, like GitHub, to do all of these things. You have quantum photonics as well. So we have other training videos like quantum transport, quantum many-body physics, quantum matter. So these are all professors that teach these materials, and then quantum computing hardware as well, and the architecture. And then here's the quantum hardware series lectures that I deliver. So this is my contribution here through Quantum Grad and the University of Minnesota. So I made these series of lectures here, and I was hosted by these fellows. And of course, these other very helpful materials that I use. So I've used these in the past before joining the PhD program. It was instrumental. Oh, you want to see the link? Let me share. Whoops. If you want to see the link, then I can share that here in the chat. I'm not sure if you can copy that, but you feel free to have a look at that document, and you can read everything on that document. You can download it. Everything is available there. So you could actually use this to get involved in quantum hardware yourself. So if you're just a beginner, then it might take a little bit more work. But I tried to include even some like animated physics here at the bottom of this list before you get to the miscellaneous part. But here, this has a lot of advanced quantum lectures involved, but it does also include some more like beginner quantum, or should I say beginner, more like pre-quantum animated physics content as well. So that's available. These are more like optional materials, but for the rest, all the hardware stuff, they're here. You want to learn how to use an oscilloscope? Great Scott makes some really good content on that. I've seen all of these videos. That's what I'm saying. And then Blender for doing animation, for making your own figures, from Dr. Joseph Mannion. I recommend his channel if you want to learn how to use Blender. And then I also have some other books related to quantum hardware. These are all, again, free or open access literatures available. And if you're able to read all of these books or read all of these papers here that I've linked, then this is good enough. This is plenty of material that can get you involved in building the hardware. So if you can read all this, you'll have a lot to think about, and you can go apply to work in the laboratory yourself, and then say that you're familiar with all these different tools and methods. It's right here, NASA wire bonding standards as well. And then quantum hardware lab galleries, these are available. These are pictures and like virtual tours of these laboratories you can watch. It'll take you there. You can click on it. And then you can see the nice pictures in the laboratory. These are the applicable quantum degrees. Various areas. You can do chemistry-related stuff, system engineering, mechanical engineering-related material that's related to quantum, like the vacuum equipment, vacuum cryogenic equipment for quantum machines, or you want to work on the materials, the quantum materials even, or designing some kind of support structure for that. You can do the electrical engineering side, which is what I'm doing. I'm working on the nanoelectronic components to control the qubits, to interact with the qubits, and to store memory after doing readouts of qubits. You can come down here and you can see an example of the quantum science curriculum that involves all these topics to get you really, really situated and familiar with the methods that are used for building quantum machines. So you can learn all of these topics here to do quantum hardware engineering even. And if you want to do quantum theory, focus just only on the theory side, then you can also do that with these resources as well. It's optional. And then here are the quantum career opportunities. So these are quantum job resources that you can see how to do it. And then this other document here, IEEE document, this is more like a coverage of the known quantum job resources, and also there are quantum jobs you can do that don't necessarily require you to be a specialist in quantum hardware or even a quantum expert yourself. You just have to be willing to support the endeavors of the quantum engineers and the quantum scientists, and you can work with them as a result. So you can consider that more of a supporting role, or as a role that hosts the work of quantum scientists and quantum engineers in the laboratory and in the field. So that's what this document covers. So this basically gives you a lay of the land, a general idea of what is possible in the quantum job industry, in the quantum industry, and also in the academic environment as well. It's applicable. And then I also have some other resources here. These are all general, really general opportunities, internships even if you want. And then they're more serious jobs. They're here. So you can do that. And then this is like a review of the physical qubits that we have currently. And this is borrowed from the document. And then the Creative Commons license that Olivier has shared. So that's what this document is about. It's here to be resourceful, to help you learn as much as you can, so that you can do things with quantum hardware yourself. Get your hands involved. And let's see here. I can show the GitHub as well if you're interested in that. So the GitHub is pretty much some of the content there, but more in a repository that you can learn from as well. Anyways, I think I've been streaming here for like almost an hour. I will allow the chats to replay. Then everyone can see what people are commenting. I totally missed many of the comments already, but I really hope I really hope that people will be able to see that those questions have been answered. Yeah. I just wanted to do that today. Another day I will come by and I'll talk about some other topic. Like I said, maybe a bit more depth on the, let's see, what else was I trying to cover? Oh, a bit more in depth on the Creative Commons motivation, the motivation for using Creative Commons as a way to really ground your designs, get your name out there. Yeah, we'll get there. No worries. So, thanks for tuning in and sticking around. I will head out, probably take a nap. It's 5 in the morning right now. I've been up for a while. I'm usually working on something. Sometimes I go to the laboratory around this hour and build some chips for some serious projects that I'm working on. Some publications. I have some publications I'm working on right now. So yeah. All right, take care out there. See you around. Ada Julia, as we say in Navajo, means to take care.